Hey, this is Gus from 3deeplearner.com, and in this short video I'm going to talk to you about autoencoders. If you have been paying attention to news in the CG world, you probably heard about autoencoders before. They have been used for denoising ray tracing and also to create super resolution or upscale the resolution of images. These are two images from slides of NVIDIA presentations where they clearly state that they use this kind of technology to address these problems. And of course, we can use autoencoders not just for images, but for any other type of data. I'm going to talk to you a little bit about what are the applications of autoencoders, and I'm going to show you an example that you can follow along in a tutorial that I have created. So this is a diagram of what an autoencoder is. It's a simplified version of it. And I found this in the Asimov Institute site, where they have diagrams for all sorts of different network topologies. I really recommend you go there and check it out. It's really nice. So as you can see right here, we have an input and output. And what makes an autoencoder is the fact that the input and output are exactly the same. You have the same data sample you use for one, you use for the other. And you may ask, why would someone want to do something like that? There's basically two applications. The first one is data compression. You can have reduced size of neurons in the hidden layer. So you create a new representation based on the data that is more compact. And the other application is the fact that since this new representation is built using the data, it will try to recreate the inputs from patterns it has learned to recognize. So this kind of gives you for free some denoising properties. As you can see right here in this diagram, the number of neurons in the hidden layer is smaller than the ones in the inputs and outputs. And the reason for that is that if you were just to put the same number of neurons or even more neurons, the network would just learn to pass through the values. It wouldn't learn anything. And it would be pretty much the same original representation. So this is kind of a limitation of autoencoders, but this can be overcome with something that's called sparsity. So here we have a diagram of a sparse autoencoder, where we have more neurons in the hidden layer than we have in inputs and outputs. And one way to do this, to add sparsity, is to add a penalty in the loss function. So you make the neurons that have higher activation, they will stay pretty much the same, but the neurons with lower activation, they will be diminished. And this helps separate the features better, and in this way you can have more neurons in the hidden layer, and the network will learn different things. So it removes this gap we have in the dimensionality of this alternative representation. Another way to do this is to add some noise. So in the Asimov Institute diagrams, this triangle represents noise. So another way to do this is to noise your data, you corrupt it, at least the inputs, and then the network will have to learn the relationship between this data and the missing parts of the data. So it also makes it possible to increase the number of neurons in the hidden layer. So these are two ways to add sparsity to your training. I'm going to show you an example of using these autoencoders to both compress and denoise MoCap data. Okay, I'll show you right here. So here's a little diagram I created based on those diagrams. We will have a MoCap that's going in, and we want a MoCap to go out, and we want to compress the representation by half, and then half of the half. So we'll be compressing this by a factor of 4. Okay, so I have explained this in a tutorial, which is right here, compressing denoise MoCap with autoencoders. And if you follow it, what you should build is something like this. We'll build a node that is going to load CSV data to matrix format, so we can control a rig from a CSV file. And okay, this is the original animation. It's from the CMU dataset. And I can press a button right here, and it's gonna pass this data through an autoencoder, which I'm loading right here. And you can see I have a similar pose, but that is being compressed by a factor of 4. So right here, if I press play, you obviously can see that it has error. It's not the same as the original, but it's being the compression, the representation is being reduced by a factor of 4. Okay, so to do this, I have created this Jupyter notebook. You can follow along, where we create the network topology. Basically have 2 neurons for encoding and 2 hidden layers for encoding and 2 for decoding. And here you can see I get a random sample from the data set, and here the transformations are represented as quaternions. We have 120 dimensions, and then we compressed all this information to only 30 dimensions. So this is the result of that, okay? And since this is an autoencoder, we can expect it to denoise our data, because it learns a representation based on the information that we have given it. So if I add noise to this, for example, let's find a more ugly pose right here. So this is nothing like anything we have seen in the original data set. If I pass this noisy data through my autoencoder, it's gonna try to fit that to something that it has seen before. So if I autoencode, it's gonna bring the actor to a much to a pose that matches closely the data set we have given it. So if I press play, you see there is a lot of noise, but if I remove this, there will be a lot more noise. So the autoencoder helps a lot. Okay, this autoencoder is very simple. We are not taking into consideration, for example, the temporal aspect of the movement. We are autoencoding just the information at any given frame. So it's not the ideal for this situation. So it's the simplest case we can have. Okay, so this is one autoencoder, as I said, that has this limitation of needing a hidden layer that has less neurons than the input and output layers. If we try to build a autoencoder with sparsity, we can have more layers, more neurons in these layers, and this makes the results a little bit better. So if I change the model to a model where we expand the number of poses with sparsity, we get a much better representation of the movement, still different, still some error, but much better representation. And it also denoises better. So if we have like some noise, turn this on, we get a much cleaner representation. Still not perfect, but better than the one where we reduce. Okay, so this is how we introduce sparsity in Keras. We get a regularizer and we add it to the layers we want to have sparsity in, and then we just train it as we would any other network. Okay, so if you want to check this out, how you can load the data, MoCap data using CSVs, and how you can auto-encode this data, I recommend you look at this tutorial. And if you have any questions, please let me know. I'd love to help. Okay, thanks for watching. If you like our video, please subscribe to our channel, like the video, and share the links on your social media. This helps us a lot. Until next time, cheers!